This is module number 4 from my online Introduction to Tensors for Non-Mathematicians course. The video, this one, returns to a question we asked previously, and that's what is a tensor? Unlike the intro video that addressed this question, here we're going to tackle it in more formal terms. We'll define a tensor in terms of the new theory that we picked up from modules number 2 and number 3. As the overall course title suggests, these videos are aimed at scientists and engineers with some background in linear algebra who want to learn more about tensors. This module is pretty focused, and it elaborates on a specific definition of a tensor, which I can go ahead and just state here. It's an algebraic object that describes a multilinear relationship between other algebraic objects within a primal space. This object is invariant to change of basis. One example we've already shown was axis rotation. Furthermore, its components react to change of basis in some special and predictable manner. Now, I know that's a mouthful. What we're going to do in this module is break that down and explain exactly what each piece of that definition means and try to elaborate upon it as much as possible. I have written a text to accompany these lectures. A link to that text will be provided in the description below once it's publicly available. I'm still working on the publisher. If you have any questions or corrections, feel free to put them in the comments section, and I will try to address them as quickly as possible. As always, please like and subscribe to see more engineering and general STEM educational videos. Let's answer the question now of what is a tensor, and this is a question that we've posed previously. So, in the introduction, we already employed an example to demonstrate the difference between a traditional matrix and a tensor, and I think that was a pretty good demonstration. We know that a matrix represents a value or a mapping whose fundamental, most true value is dependent on some assumed set of axes, referential directions, and or basis. The tensor is similar, but the axes, the basis, the referential directions are not assumed, and they're explicitly stated within its definition. And this is the reason why, if we look at those two models, right, we had the matrix system definition and the tensor-based system definition. And for the matrix, for the tensor-based definition, we were able to incorporate the rotational matrix and account for the change in that observer's point of view. Whereas we can't necessarily do that for the matrix-based equation unless we make some assumptions. Now, here in this section, we are going to expand upon the definition provided that example to represent the tensor as, and we're going to read this through one time and then we're going to break it down into its parts. So it's an algebraic object that describes a multilinear relationship between other algebraic objects within a primal space while remaining invariant to change of basis. And you can see here I've coordinated the colors of these clarifications or these additional details with the colors of the parts of the statement from up above. Okay, so let's break it down. It's an algebraic object because we know that the tensor is some structured set of numbers, and that was the definition we gave for the algebraic object in the beginning. So check. All right, multilinear relationship. We know that our tensor, the objective, is to describe some relationship, some mapping. That could be like a linear map where that describes, going back to our example, how the velocity VA changes to become velocity VB over the span of a single time step, or it could be something like a primal vector, which is simply just defining an inherent physical related value and how that is projected to its axes. Okay, so check. Third, within a primal space, now why are we worried about or concerned with relationships between algebraic objects within a primal space? Specifically because the primal space contains those physical values, and generally we want to define relationships between physical-like values, and that means that they will be within a primal space. And then finally, it should be invariant to change of basis, and this is perhaps one of the most important aspects of the definition of a tensor, is that it should be invariant to change of basis, right? The value of the tensor, unlike its components, should not change if the axes are manipulated, the referential directions, the basis. So the components may change, but the tensor itself does not. In short, a tensor is a matrix or an array with its associated bases embedded within it. All right, so this slide here provides probably the most concise, most formal definition of a tensor out of the entire set of these lectures. And we do so in terms of three characteristics. So there's three characteristics that we need for our tensor to have or to satisfy. And there is some repetition between this and what we just presented on the previous slide. I apologize for that, but I think it's important to describe this in maybe two different ways. So a tensor should describe a multilinear relationship, right, between sets of algebraic objects within a primal space. And we've kind of already explained this, right? It should be a multilinear relationship because that's generally how we use tensors, right, to describe some sort of mapping between algebraic objects, because the tensor is a structured set of numbers as well as the vectors it maps to and from are structured sets of numbers, and within the primal space, because the primal space is what contains those physical-like values that we're concerned with. One example is a linear map that defines the relationship between two, and I can write here, primal vectors. Now second, so that's the first characteristic. Second is it should be invariant to change of basis. Okay, so the value of the vector, or of the tensor, sorry, I should use the word tensor here, is invariant if to change of basis, meaning that if we change the axes to which the value is projected, or we change the referential directions, or of course change the basis, the tensor value does not change. It's fundamental. So although the tensor is a product of coefficients and basis, right? We can use the vector example, v arrow hat is equal to b arrow hat times some sort of array, coefficient array right here. The most fundamental definition of that tensor, which is this guy, okay, it is inherent and unaffected by change of basis. It is fundamental. It is a fundamental definition of that value. And so let's go over here, and I want to draw a little bit of a picture that tries to exemplify this idea in terms of the example from the first module. All right, so let's say we have a kind of a superposition of two different situations. We have a flat piece of land, and then we have a sloped piece of land. Okay, and we have someone over here who's going to throw this ball. Okay, it has some trajectory. It starts off with a velocity that is referred to as VA arrow hat. That's the tensor. And we could, if we wanted to, break that down into B sub A arrow hat times VA. Okay. Then over here on the observing side, let's say we have two different observers. Okay, we'll call this observer 1 and we'll call this observer 2. Now, what's the difference between these two? They have, first off, they have different basis sets, right? They are oriented with respect to different axes. So we'll call the axes of this first observer, I think we previously called it B sub B. And then this one over here has a rotated set of axes, and we refer to that basis set as B. I don't know if I'm going to have room for this, post B. Okay, so this is the basis set associated with user number 1. This is the basis set associated with observer number 2. And they are rotated with respect to one another. Now, with regard to the observations, what they observe will be the movement through their respective axis directions. So this observer number 1 is going to observe a value that we call VB, okay, with no arrow hat. And that is its movement through the X, Y, and Z directions. Observer number 2 is going to observe something that I'm going to call V post B. No arrow hat again. And that's its movement through what we previously called the P, Q, and R directions. So the two observers, they have different basis sets, different referential directions, different axes. And as such, they observe different movements, okay, through their respective directions. But the fundamental motion of the ball on the secondary side, which we're going to call VB arrow hat, is unchanged, right? The difference in their orientations and their points of view does not affect the true value of the velocity of the ball after that small time step. And so what we see is that that is equal to B sub B arrow hat times VB, which is equal to B post B arrow hat times V post B. And neither of these have arrow hats. All right. So although our components can change, right? We can rotate our axes, and those rotations will cause them to observe different values. In the end, the tensor with the arrow hat, okay, that is a fundamental value that cannot change. And that is what we're trying to say here with that second bullet. Okay, the tensor is invariant to change of basis, manipulation of the axes, or any change in the referential directions. It's the product of two components, right? The coefficient array and the basis, both of which may change, but the resultant tensor does not change. If we scale B up, the coefficient array must go down. All right, so this is probably the most important characteristic. And then the third characteristic is that the tensor should have components that are predictable under change of basis. So these components, the basis set and the coefficient vector, we just said a second ago that they do change. Right? They do change if we change the orientation of the observer or something similar. And they do so in a special and predictable way. We should be able to use some theory to update B as well as V such that the value of V arrow hat is maintained. So we can define a tensor, right, using any infinite number of different basis sets. We already saw this by our example where we have the decline in the ground, right? We can define an infinite number of theta values of inclines or declines of that ground, which would change the observer's point of view. So I think this picture right here does a very good job of, although it's not necessarily aesthetically pleasing, does a very good job of explaining why the tensor value is fundamental and inherent, whereas the individual components, okay, the basis as well as the coefficient or the coordinate rays, are not. The next module formalizes our understanding of covariant change of basis, how this type of transform may be applied to basis sets and their associated coordinates, as well as how this transform may be reversed. It clarifies some theory that we've used in previous modules, but perhaps we haven't fully explained. A link to that next lecture is available in the description below, or will be available very soon. I look forward to reading your questions and potentially some corrections in the comment section.